Hi, I'm Mark Barsamian. In this video, we'll be discussing conditional statements. The reading for this video is in section 2.2 of Epps' book. So we'll start with the definition of a new compound statement form. Compound because it will contain more than one statement variable. First of all, the symbol. There are two symbols that are widely used. The first is P arrow Q, and the second one is this one, if P then Q. I write the if and the then in capital letters. Of course, it's spoken, just if P then Q. Less commonly spoken is the following. The conditional of Q by P. I've actually never heard anybody use that phrase, except that this statement form is called the conditional. The usage is, of course, that P and Q are statement variables. Now, finally, the definition. This symbol, P arrow Q, or these words, if P then Q, denote a statement form. Now, remember that a statement form is something which becomes true or false when actual statements are substituted in for the statement variables. So if somebody's going to sell you a statement form, they have to tell you how it's going to behave, how it will become true or false, depending on the different values of P and Q. So this statement form has truth values that are going to be defined by this table. The truth of if P then Q goes as follows. So if P then Q is true in all cases except this one. The only time if P then Q is false is when P is true and Q is false. Some additional terminology goes with this definition. The P symbol, or whatever is sitting in that spot, is called the hypothesis, and the Q symbol, or whatever is sitting in that spot, is called the conclusion. Let's start with an example. Which of these statements is true? The first statement is, if 4 is an integer, then Thanksgiving is in November. And notice that the word if and the word then are all caps, indicating that these words are being used in the logical sense, in the sense that we've defined if then. Well, notice that this sentence here, 4 is an even integer, is true. And this sentence, Thanksgiving is in November, that's also true. So what we have here is true, arrow, true. If true, then true. Now we know that that is true. From our table, we have a case of this. True, arrow, true becomes true in that case. Question B. What about this sentence? If 4 is an even integer, then the world is flat. Well, notice that the sentence 4 is an even integer is true, but the sentence the world is flat is false. So we have a situation where we have true, arrow, false. That's false, according to our table. True, arrow, false is false. What about this third example? If the moon is made of green cheese, then Thanksgiving is in November. Well, notice that this sentence, the moon is made of green cheese, is false. The second sentence, though, is true. Thanksgiving is in November is true. So we have a situation where we have false, arrow, true. Well, according to our table, false, arrow, true is true. And finally, this last example. If the moon is made of green cheese, then the world is flat. Well, this sentence is false. And this sentence is false. The world is flat is a false sentence. But when I put them together like this, I have false arrow false. And that is true. So again, we notice that the only time that an if-then statement is false is when the hypothesis is true and the conclusion is false. There's a special term for this kind of situation that we have in these last two parts of the example, where the conditional statement is true just by virtue of the fact that its hypothesis is false. Look at the table up here. Anytime the hypothesis is false, the conditional statement is automatically true. It doesn't matter what the conclusion is doing. As long as the hypothesis is false, anytime the hypothesis is false, a conditional statement will be true. Well, that kind of situation is called a statement that's vacuously true. Now, we now have four logical symbols that we're going to be using. We have seen the wedge, the V, the arrow, and the tilde. That is the and, the or, the if-then symbol, and the not symbol. We also have the exclusive or symbol, but we won't be using it. So the question is, what is the order of operations for these symbols? Well, the order of operation is as follows. Whatever is in parentheses is done first, then the negation, then the and, then the or, and finally the conditional. Let's do an example. Construct a truth table for this statement form. Now notice that that statement form involves three statement variables, P, Q, R. So we are going to need 8 rows. And we will need a column for each of those variables. And remember how we populate those columns. We start with the rightmost variable column, and we go down that column alternating true, false. Then we move over one column to the left, and we go down this column alternating true, false, but going 2 rows at a time, true, true, false, false, etc. Then finally we move over one more column to the left, and we again go down that column alternating trues and falses, but again half as fast as what we just did, so 4 trues and then 4 falses. All right, now how do we populate this table? Well, looks like I need one more column here. The first thing that we do, well, let's add some parentheses to make it clear how we will compute this. The first thing that we will do is we will compute the negation of Q. Once we have the negation of Q, the next thing that we do is the and. Only after we've done those two things do we finally do the conditional. So let's put in a column for the negation of Q. We'll have to figure out the values for that. Once we have the values for the negation of Q, then we can compute the values of P and the negation of Q. And finally, once we have that, we can compute the conditional. So to compute the negation of Q column, we simply take the values in the Q column and we negate each one of them. Now, to compute the values in the P and negation Q column, we investigate the P column and the not Q column, and we do the and of those two columns. Now, to compute the final column, we need to take the conditional of this column, or we need to do if whatever's in this column, then whatever's in that column. So here we need to be pretty careful about what we're doing. So notice that the columns appear left to right as true on the left and false on the right. But remember, we're taking the if of this column and the then with this column. So it helps to write them in the order that you're actually considering them. There we have it. There are the truth values of our statement form. Now I'd like to discuss expressing the conditional statement form in an alternate form. So the job is to use a truth table to prove that if P then Q is logically equivalent to this, not P or Q. So this is, both of these are statement forms involving two variables. So we need 2 times 2 is 4 rows, and we'll need columns for each of the statement variables. And remember how we populate those. We start with the rightmost variable column and alternate true, false. Then we move one column to the left and alternate true, false, 2 rows at a time. Now we need a column for this statement form, so we can just label one of these columns with that symbol. And we need a column for this statement form. Now remember, the order of operations for this second statement form are actually the following. According to the order of operations, the negation gets done first. So before we can compute this statement form, we need to compute not P. So we make a column for the negation of P. So we populate this column by looking at the entries in this column and negating each one of them. All right, we populate this column by doing if then on these two columns. There's our column of truth values for that statement form, if P then Q. And I should make that Q lowercase because it is a statement variable. Remember, capital letters usually represent entire statement forms. Lowercase letters are statement variables. Now we're ready to compute the data for this column. So we need to take the OR of the not P column with the Q column. It doesn't matter which order we do that in. So there's our data for that last column. Now, remember, our job was not just make a truth table, but to use it to prove that these two statement forms are logically equivalent. So to do that, we have to make the truth table and explain clearly what it tells us. These two columns match, so the statement forms are logically equivalent. That's the end of that example. Now, once we have this information that if P then Q is logically equivalent to this other statement form that uses more primitive symbols that we knew about in the previous video, the negation and the OR, once we know that stuff, we can use De Morgan's law to find the negation of the conditional statement. So remember that when using De Morgan's law, it sort of looks like the distributive law, but you're not distributing. But these green arrows denote that this negation affects all three of the things in this expression. It affects that, it affects that, it affects that. The or changes into an and. So we've found that the negation of if P then Q is this expression, P and not Q. So let's summarize what we have found because it's very important. The negation of the conditional statement form, the negation of the if then, is the following. For this conditional statement form, P arrow Q, also spoken if P then Q, the negation is this statement form. That is, the negation of if P then Q is P and not Q. And very important thing to notice here, the negation of a conditional statement form, the negation of an if then, is an and statement form. You don't get another if then statement when you take the negation. So let's do a couple of examples. For this statement S, if today is Saturday, I go to Kroger today, find the negation. Well, you could think of this as our P and this is our Q. So this is of the form P arrow Q. So the negation of this will be P and not Q. So the negation reads, today is Saturday and I do not go to Kroger today. This is a good example to think about the meaning of the negation and the meaning of the conditional and why it has this strange behavior. You should think of a sentence like this as a sentence about the situation that today is Saturday. It says something about what happens on Saturday. I will go to Kroger today. It doesn't say anything about what happens on any other days. So if I happen to go to Kroger on Wednesday, I haven't lied. All I said was, if today is Saturday, I'll go to Kroger today. If today is Wednesday and I don't go to Kroger, I still haven't lied because I never said anything about what's going to happen on Wednesday. So the only situation in which I would have said a lie in saying these words would be this situation. The only situation when I would have lied would be the situation where today is Saturday and I don't go to Kroger today. So it doesn't matter what happens on any other day of the week. I could go to Kroger or not, and it would not mean that I lied. Now let's negate this statement. If Bob is green, then Carol is red. So we could think of Bob as green as the P, the hypothesis, and Carol is red as the Q. So the negation would be Bob is green and Carol is not red. So again, notice that the negation is an and statement. It is not an if-then statement. Now I want to talk about related conditional statements. So for a given conditional statement, if P then Q, or P arrow Q, we introduce these related conditional statements. The contrapositive of S is denoted this way, contrapositive parentheses S, and it means this statement form. Negation Q, arrow, negation P. So if not Q, then not P. The converse of S is this statement form, Q arrow P. So if Q, then P. The inverse of S is this statement form, if not P, then not Q. So for an example, let's go back to this conditional statement. If Bob is green, then Carol is red. Let's write the contrapositive, the converse, and the inverse. So the contrapositive, remember, if we think of this as P arrow Q, then the contrapositive is not Q arrow, not P. If Carol is not red, then Bob is not green. The converse, remember, is just simply Q arrow P. And finally, the inverse. The inverse is not P arrow, not Q, which is written if Bob is not green, then Carol is not red. Now I want to talk about the logical equivalences between the original conditional statement, the contrapositive, converse, inverse, and the negation. So suppose that we have a conditional statement form, P arrow Q, if P, then Q. So that's our original. So the job is to make truth tables for that original statement form. It's contrapositive, it's converse, it's inverse, and it's negation. So start with making two columns for the statement variables. Now, we know that in order to build these things, the contrapositive, the inverse, we're going to need the negations of P, Q. So let's build those. So we're going to need those at some point. Now let's put columns for each of these things we've been asked to build. So there are our four columns. Now remember how we populate these. We start by populating the columns that have the statement variables, starting with the one on the right, alternating true, false every row. Then we move one column to the left and populate that row, alternating true, false, 2 rows at a time. Now we populate the not P column by taking the negation of all the things in the P column, obviously. And we populate the not Q column by negating everything in the Q column, obviously. Now we're ready to go. We populate this column by doing if P, then Q. So that's the data for the if-then statement that we saw a couple of screens ago. Now we're ready for the contrapositive. Now to build this, we have to be careful. We have to do not Q arrow P. So there is the data, and up above I've, for just a minute here, have left the thinking that went behind computing all those values. Now let's move over to the converse column, Q arrow P. So for this, we need to do the OR in this direction. So let's compute those values. And again, I'll show the computations above. So there is the column of data for the converse, and you can see how I computed it. Now move over to the inverse column. We compute inverse of S by computing not P arrow, not Q. So here are the computations. There's the column of data for the inverse, and you can see how I computed it above. Finally, we compute the inverse. of S. Now to compute that, we simply look at this column and we negate it. Now some important observations to notice about this result, this table. First of all, notice that S and contrapositive S are logically equivalent. These two columns match. And notice that converse S and inverse S are logically equivalent. But notice that S and the converse are not logically equivalent. These columns don't match. They differ in these cells and they differ in these cells. Also notice that inverse S and negation S are not logically equivalent. These columns don't match. That's important because a lot of people get the language confused. I mean, we're used to the idea that in some situations you have, like the additive inverse of 5 is -5, the negation of 5. So in some settings, the word inverse can mean the same as negation. But the multiplicative inverse of 5 is not the negative of 5. The multiplicative inverse of 5 is 1/5. So inverse and negation don't, already in what we've learned in math before, they don't always agree. They don't mean the same thing. So inverse and negation are not the same thing. And it also brings up another word that's often misused, the word opposite. So if you say the word opposite, some people will think, well, maybe you mean inverse. Other people might think, well, maybe you mean negation. Well, those things are different. Inverse and negation mean different things. We don't have the word opposite in our vocabulary of terms for this course. So we use the word inverse to mean one thing, and we use the word negation to mean something, but those two things are not the same thing. And in fact, notice that the negation of S is not logically equivalent to any of the others. So this last column of data doesn't match any of the other columns. Another incredibly important fact is this fact that I mentioned before, that S and contrapositive S are logically equivalent. This is extremely important in doing proofs. It's often overlooked. Now I'd like to turn our attention to kind of reversing this process. Suppose that we know that this statement form is true. What are the values of P, Q? Well, remember that the statement form, if P then Q, has this truth table. So if we are told that P arrow Q is true, it could be this situation, it could be this situation, or it could be this situation. So P and Q could be true, true. PQ could be false, true. And they could be false, false. So we don't know the values of PQ. We know that there could be any of these three combinations. So then what would be the value of Q arrow P? Well, let's see. In the green case, Q arrow P would be true. In the red case, the result could be false. And in the black case, the result would be true. So we don't know the value of PQ from knowing that P arrow Q is true. And so we don't know the value of Q arrow P. Now suppose that if P then Q is known to be false, what are the values of P and Q? Well, let's go back and look at that table again. Notice that the only time that P arrow Q is false is this row when P is true and Q is false. So now the question is, what's the value of Q arrow P? So Q arrow P would be true. So let's reiterate what we've just observed. So knowing that a conditional statement is true does not nail down the values of its statement variables, and so it does not nail down the value of the converse. But we just observed that if we know that a conditional statement is false, then that does nail down the values of the variables. So knowing that a conditional statement is false does nail down the value of its variables, and so it does nail down the value of the converse. The last topic for today is translating common language into conditional statements. So what does this sentence mean? I will have a cookie if today is Saturday. Notice the if is not at the beginning of that sentence. It's in the middle. So this is a sentence about the situation of today being Saturday. It tells us something about that situation. It says, if today is Saturday, then I will have a cookie today. So that's what it means. So let's generalize this. The words P if Q, notice I've written the if in lowercase, have this logical form. If Q, then P. And notice that I've written these words in capitals, so I'm using the if, then in the logical sense in that sentence. And the symbol for this is Q arrow P. What about this sentence? What does I will have an ice cream today only if today is Friday? What does that sentence mean? Well, it's about the situation where I have ice cream today. It says in that situation, I know for sure that today is Friday. So what this is saying is, if I have ice cream today, then today is Friday. So we can generalize this. These words, P only if Q, have this logical form. If P, then Q. Capitalizing those to draw attention to the fact that we're using if then in the logical sense. Now I want to talk about translating if and only if into conditional statements. So consider this sentence. I will go biking today if and only if today is Wednesday. What does that mean? Well, let's let be the phrase I go biking today, or I will go biking today. And let's let W be the phrase today is Wednesday. Then sentence S could be abbreviated be if and only if W. But that means be if W and be only if W. But remember that those phrases, be if W and be only if W, have representations in logical symbols. So this sentence that we started with has representations in logical symbols that looks like this. Now, here's a question. How would this statement form that we've just built behave? Well, let's investigate with the truth table. We need a column for B, W. We need a column for B arrow W. We need a column for W arrow B. And finally, we need a column for the AND of those two things. So we populate the W column first, alternating true, false. Then we populate the B column, alternating true, false, half as fast. And then we populate the other columns. B arrow W, remember that's true in all situations except the situation where B is true and W is false. So that row gets an F, all the other rows get true. Now let's move over to the W arrow B column. That's going to be true in all situations except the situation where W is true and B is false. That's this row. So that row gets a false and all the other rows get true. Finally, to populate this column, we take the AND of these two columns. So notice that this column is true in exactly those rows where B and W have the same truth value. In the first row, B, W are both true, and this rightmost column is true. In the last row, B, W are both false, and this column is true. This brings us to the definition of what's called the biconditional. So the symbols are P double arrow Q is one symbol, and PIFFQ is another symbol. And this is spoken P if and only if Q. It's also spoken less commonly, the biconditional of P and Q. And what it means is, it means if P then Q, and if Q then P. But a clearer meaning in words would be just simply to say that P, Q have the same truth value. Finally, translating other common language into conditional statements. What does this sentence, P is sufficient for Q, what does that mean in terms of conditional statements, if then? And what is this sentence, P is necessary for Q, in terms of conditional statements? How would you express that? Well, the book explains this quite well in section 2.2. Epp's book really does a wonderful job of that. And you have a couple of exercises about it in the homework. So I'm going to leave it to you to read the book for the discussion of this and work on those exercises. So that's the end of the video. Good luck with the homework.